This video is to show you how to do the reverse tabular method. The reverse tabular method. And this is a method we use to divide polynomials. I'm going to show you an easy example and a difficult example. First, the easy one. 2x cubed plus 11x squared plus 2x minus 15 divided by 2x plus 3. Now, there's multiple ways we can do this, and one of the ways we could do this is called the reverse tabular method. So if you're watching this, then you should have also seen the tabular method, which is how we can multiply polynomials using a table, basically, using boxes. So doing it backwards like this is a little different, but it's really a great method, and I think you're going to see why, because it has a lot of built-in features that keeps you structured and organized and also checks your work as you go. So, especially at the end. So let me get started here. Now, the numerator here, this is called the dividend, and the denominator is the divisor. And what we're going to be looking for to solve is the quotient. And so the way we set this up is don't worry about how many columns your table is going to have. The problem is going to dictate that as we go. But you do need to know how many rows you have. But really, before you do anything, you should take a look at the dividend and the divisor, the numerator and the denominator, and see if there are any, what I call holes or gaps in the problem, any missing terms. You see, my lead exponent, my highest exponent in the numerator is x to the third. So I want to make sure that I have an x to the third term, an x to the second term, an x to the first term, and then a term without an exponent, which we call a constant. So it goes 3, 2, 1, none. Our numerator has all the terms it needs. Our denominator's highest exponent is 1, so I just need an x to the first term and a constant. I have both of those. So there are no gaps in the exponents for each term. And they are written in standard form, exponent descending order. You need to check both those things. If it's not in order, you got to put it in order. And if you have any gaps, well, then there's different things you could do, but I'm going to show you my method to avoid that from becoming a mistake. All right, so the bottom tells us the number of rows. So the amount of terms in the divisor tells us how many rows. So I see 2 terms in the divisor, so that means my table is going to have 2 rows. All right, and those rows are going to be 2x and 3. And so that's how I'm going to set up my table. I have a row for things multiplied by 2x and a row for things multiplied by 3. How many columns? Again, there is a way to tell. Real quick, I'll tell you that it's this exponent minus this exponent plus 1. But I wouldn't really worry about it. Let the problem show you how many columns. So let's just start off with 1 column for now. So the divisor goes on the left of your rows, and then that's how you tell how many rows there is. The first term of the dividend goes in your top left box, 2x cubed. And you know that's not going to have any like term boxes diagonal of it, and you should know that from doing the tabular method, the previous video or previous lecture in class, that you know there's no diagonal boxes for that top left box, so that is what it is. These other middle terms, they are going to be the sum of multiple like term boxes, multiple diagonal boxes. So our dividend ends up being in the boxes. Our divisors on the left, our quotient, the answer to this problem is going to end up on top. So because the divisor goes on the left and your first term goes in your first box, that allows you to figure out the title of the first box, because this 2x cubed comes from 2x times what? Or you could think 2x cubed divided by 2x to get this up here. And the answer is x squared, because 2x times x squared is 2x cubed. And once you have that title, now that's the first term of my quotient, I can multiply that by the rest of my rows to get the boxes below. So this would be 3x squared. And you see that my columns, top to bottom, always have exponents descending. So this is 3, then 2. If I had another row, it would be x to the first. Same thing with the rows. They go left to right, exponent descending order. This is going to be 3. This is going to be something x squared. If I keep going, something to the first, so on, so on. So that's my first column. I'm not done. My second column Now, the way I figure out this top box, and we always go top to bottom, move over top to bottom, top to bottom, is these diagonal boxes are like term boxes. That means they're both going to be x squared. Because like I said, my exponents go down, so this is going to be something x squared, but I don't know what number it is here yet. And that something x squared is determined because these diagonal boxes have to add to the terms of the dividend. So your like terms in the box, your diagonal like terms, add to the terms in the numerator, the dividend. So if this is 3x squared, and they have to add to 11x squared, that means this has to be 8x squared, because 3 plus 8 is 11x squared. And that, since I know it comes from something times 2x, tells me the title over here must be 4x, because 2x times 4x is 8x squared. Because it's positive, I'll throw a plus between them. Now, I can multiply that by 3 to get the box below. See, the boxes below we just get from tabular, from multiplying the title up top and the divisor on the left. So this is 12x. The top row we get by figuring out, all right, what like terms combine to be these like terms. So my next column, I know my diagonal like term boxes are the x to the first terms, and they got to combine to be 2x. So if I have 12x, that's going to make this negative 10x. This 12 and negative 10 combine to be positive 2. And that gives me the title up here of negative 5. 2x times negative 5 is negative 10x. And then I multiply down. 3 times negative 5 is negative 15. And what's beautiful about this method is that this last box is my last term of the dividend. And that tells me that I divided properly. And so my answer is x squared plus 4x minus 5. All right, I want to do one more for you, but this one's going to be difficult. Why is it going to be difficult? Well, take a look at it. The first thing you should notice is in the dividend, the numerator, it's out of order. Not only that, do we have any wholes? What's our highest exponent? The highest exponent is 4. So do we have an x to the third term? Yes. Do we have an x squared term? No. So we're missing an x squared term. So let's include a 0x squared. So it'll help us remember that there is an x squared term, it just happens to be a 0. Is there an x to the first term? Yes. Is there a constant? Yes. So it's out of order, and it has a what I call a hole or a gap. So I'm going to rewrite this in order. It's 2x to the fourth, and then minus 3x to the third, 0x squared, minus 12x minus 64. It's in order, and I filled in that gap with a 0 expression. The bottom, it's in order, but this also has a hole or a gap. It starts with x squared, but then it's missing an x to the first term, so it needs a 0x to the first term. So x squared plus 0x plus 4. So if you don't do that right away, if you jump right to trying to make the table or long division or whatever method you're doing, you're going to have a tough time if it's not in order and you don't recognize those gaps beforehand. Now that I know that, I see I need 3 rows down here. Even though there's only 2 terms here, but I know I'm missing a term, so I'm going to do 3 rows. I'm going to have an x squared row, a 0x row, and a 4 row. Move that over. And make my 3 rows table. Start off with 1 column. My first term, 2x to the fourth. Oh, actually, I should use it down here, and I'll switch to a different color over here. 2x to the fourth. That goes in my first box, which tells me the title must then be 2x squared. Multiply it down. Now, this is going to end up just being 0. I can write it as 0x cubed if I'd like. This way, I can still see the pattern of the exponents decreasing top to bottom, left to right, but it is 0. And it's going to get combined with the box over here as a like term, but this is 0. Because 2 times 0 is 0. And 2x squared times 4 is, of course, 8x squared. And so I see my exponents go 4, 3, 2, even though there's a 0 there. Add a column. These like term boxes are x cubes. I need a total of negative 3x cubes. And since there's 0 here, this has to be negative 3x cubed. Remember, these have to add to be these terms, and 0 plus negative 3 is negative 3. And that tells me my title then has to be a negative 3x, because that times that is this. Negative 3x times x squared is negative 3x squared. Multiply down, again, this is going to be a 0, but I can write it as 0x squared if I'd like to keep my consistent exponents decreasing left to right, exponents decreasing top to bottom. It's like, do I really need this middle row at all? The answer is yes and no. No, technically, but yes, because if I don't have that, then I might get confused about my diagonal-like terms. See, if I didn't have that, then this x squared, this 8x squared would be here, but they're not like terms. So I keep it there really just for structure. Negative 12x. Now, this diagonal pairing here has not just these diagonal two, but this one also. There's 1, 2, 3 boxes that are diagonal like term boxes. So all of those have to combine to be 0x squared. So I need all this to be 0. I have 8, 0. Then this is going to have to be negative 8x squared, so that they all combine to be my term there. And that tells me up here that this is going to be negative 8. This is 0x, and down here multiplies to negative 64, which is what I was hoping for. So my answer is 2x squared minus 3x minus 8. Sorry the video is a little long this time, but this is a lot to explain, and we will practice this a lot in class. See ya.